I also start by wishing everyone a happy and healthy new year. Let me also start with a disclaimer that I am not going to talk about my work. In fact, I'm literally following what Sushmita said about you don't have to talk about your newest work. So this is neither my work nor a newest work. But Discrete Fourier Transforms is, I think, a nice algorithmic tool, which I think is very useful. And string matching is a popular problem, so hopefully it will be of interest to most people. So again, I can't see the chat screen or anything, so please shout if there is a question or a message or anything. Yeah?
Yeah, I can relate to you, Venkatesh, if there are any
So
questions.
here is a string matching problem. You are given some text. I've written one A, B, A, B, A, B, or some finite alphabet, and the pattern P. And the question we want to ask in the string matching problem is to find all occurrences of this pattern in the text. And when we say occurrences, it's just a contiguous occurrence. So for example, this pattern occurs at 2 places in this text. And we are interested in the algorithmic question. Okay. So here is another example. If AB pattern occurs at multiple places in this text. So in particular, my output should be all the positions of the text where the starting point of my pattern appears, if at all. So this is, obviously a very important practical problem. When you're doing for a word in your text editor or in Google, this is exactly what you're doing. You're looking for some you have some query and you're trying to match it in some large text. So n is the length of the text and m is the length of the pattern, and n is very, very large compared to m. So a naive algorithm of just sliding the pattern across the text takes m times n. So for example, in this, can you also see my mouse?
Yes.
Okay, so if I can just start matching this pattern with my text, and the moment either there is an occurrence or it's not an occurrence, I just shift my pattern by 1 step to the right and start matching again. So in the worst case, I might take m times n, so that's like an mn algorithm. There's a very classical algorithm due to Knuth, Morris, and Pratt that actually says that this can be done in m plus n time. It essentially takes the pattern, does some pre-processing, builds some sort of an automaton, and then when the runs the text on the automaton, so overall it takes about m plus n time. If the real problem in most applications is that if the text is given in advance, you're allowed to pre-process the text, and so that whenever the pattern query comes, you want to answer the query in time proportional to the pattern. And there is such a very nice data structure called a suffix tree, which actually can pre-process my text. And whenever a query comes, I will answer time proportional to the length of the query, which is very, very important. When you are searching for a pattern in this Google database of tens of billions of websites, you don't want to spend time proportional to the length of the text, which is the tens of billions of the words, strings, characters, but instead this can pre-process the text and answer your query in time proportional to the length of your pattern, which is very efficient. What today I'm going to talk about is this notion of approximate string matching, where what if your pattern or the text has some don't care characters which can match with any character in the text. So I might look for B, question mark, A, question mark, A in this long text, where question mark can actually meet with any character. So this is one among many questions one looks at in this area of approximate string matching. And I'm going to just give this simple version of this problem and talk about how we can do it. Now, it turns out this Knuth Morris Pratt algorithm cannot be easily modified to make this question work efficiently. And more than talking about this problem, my interest is to actually tell you about this discrete Fourier transform technique. and more how that is a nice algorithmic tool, and then we will use that to solve this problem. So let me get to discrete Fourier transform. So it's a transform. It takes an n-dimensional complex vector and transforms to another n-dimensional complex vector. Okay. Now this is related to whatever Fourier transform you would have seen in signal processing and various other things. But let me just stick to my definition and work with that. And so, in other words, what is this transform? Look at this Vandermonde matrix. This matrix actually came in the previous talk, Ajit's talk as well. So this has the ijth entry is, omega n is the principal nth root of unity, and ijth entry has actually omega n power I times j. And what this transform is that this Vandermonde matrix.
Venkatesh, you had a question.
Yeah.
Venkatesh, I just had a question for the. Can you hear me?
Yes. Yeah.
Yeah. Hi. So for this partial string matching problem, is it? Should the question marks, is it required that they be only in the middle of the string, or can also be at the end? Are there some restriction on what you do not care, the positioning of that?
They can be anywhere, but they actually
can be anywhere.
Yeah, but they should match one character. It is not, they cannot match a whole substring or something. Question mark is actually matching one character.
One character. Okay.
So for example,
thank you.
What I want is BBB and then some two other characters, which could be anything, and then AB. So that's what it is.
Okay, thanks.
Yeah.
Thanks.
But they cannot appear at the beginning, is it? Because you don't know where the string begins then.
It can, no problem.
So you know which characters are those don't care characters.
Yes, exactly. You're given. Yeah, it's a specific question. Yeah. Okay, so what is this discrete Fourier transform? It takes this vector a0 to a-1, and you post multiply by this Vandermonde matrix, which has the ijth entry, the cube nth root of unity based on that, and what you get is this vector b0 b1 minus 1. Okay, so this is the discrete Fourier transform of a0 to an minus 1 is actually b0 to bn minus 1. Okay, as the Vandermonde matrix is invertible, this transform is also invertible. Given the bi's, you can also compute the ai's. Okay. Now, a naive way to compute this, because we are algorithm theorists, we care about how much time it takes. Naive way to compute this transform is actually n square, because to compute one bi, what you do is you take one row and multiply by this vector. So there are n multiplications. That takes you n time to compute one bi, and there are n bi, so it takes n square. What makes it useful for algorithmic purposes is that actually you can compute this in n log n time. And then this could be a big difference when n is very large, because when n is like 2 power 50, n log n is, log n is just 50, because n log always is to the base 2 for us. And n is 2 power 50. So it can make a big difference. And how do we do it? We use, I'm actually going to tell you in this slide how to actually compute the transform and its inverse in n log n time using divide and conquer and properties of the roots of the unit. Okay, so one way to think of this transform is look at this polynomial, univariate polynomial of degree n. So remember a0 to an minus 1 is the vector which we are trying to transform. So then the transform is essentially evaluation of this polynomial on all the nth roots of unity. Because if you think of this matrix, what is bi? You take the first row and multiplying by first row, this column, it's same as saying this polynomial evaluated at 1, 1, 1, 1, 1. And then the second entry ba1 would be this polynomial evaluated at 1 omega n square, omega n cubed, and so on and so forth. So essentially this transform can be also considered as evaluation of this polynomial at nth roots of unity. Now look at this polynomial. I'll tell you how to break it up into two polynomials. So let me take the even terms of this polynomial alone. a0 and a2x. I'm not putting a2x square, just put a2x, a4x square, and so on and so forth. And then take the odd coefficients of this polynomial, and I'm writing a1 plus a3x plus a5x square. Then it's not very hard to see that this polynomial ax is nothing but ae evaluated at x square plus x times ao evaluated at x square. Okay, so what have we done? Well, we have broken the computation of this n-degree polynomial into computation on two polynomials of about roughly half the degree. And we want to, instead of evaluating an x, you are evaluating at x square. But the beauty of this nth roots of unity is that the x square, if you take the square of the nth roots of unity, first of all, they are not n of them, there are only n by 2 of them. Okay, I'm going to assume that n is a power of 2. So when I say n by 2 and all that, it's an integer. So when you take the squares, they are actually n by 2th roots of unity. N by 2th roots of unity. Okay, so that's a property of this roots of unity. So what happens is evaluating a at nth roots of unity is now boiled down to evaluating two polynomials of about half the degree, evaluating at half roots of unity, half the number of points. So this gives us a nice recurrence relation, and T of n, computing this n evaluations of this polynomial, is 2 times T of n by 2 plus order n, which solves to n log n. It turns out the inverse transform also can be, take the van der Maan matrix, look at the inverse of this matrix, and inverse also looks like evaluating some polynomial on some n roots of unity. So it can also be computed in a very similar fashion in n log n time. Okay. So what I have told you is what is a discrete Fourier transform. It takes an n-dimensional vector, multiplies by this van der Maan matrix, gets another n-dimensional vector, and this matrix, this transform naively takes n square time, but in in very, very clever use of divide and conquer, you can actually compute it in n log n time. Okay, so what are some applications of this? I mean, I'm going to get to the string matching application, but before that, it's, as I told you, it's a very powerful algorithmic tool. So let's see what. First application is that two univariate polynomials of degree n each can be multiplied in n log n time. What do I mean by that? So here is a polynomial of degree 10, a and b I have written, and suppose I want to compute the product polynomial. You know how to do it. You look at coefficient by coefficient. If I want to compute the coefficient of x power 10, let's say, then from a, you look at a constant term, multiply by the coefficient of x power 10 in b, and then take the x square term and x power 8 term, x cube term and x power 7 term in b, and so on and so forth, and multiply by them, and you get the coefficient of this product, a particular coefficient. So there are 2n different coefficients. In fact, you can easily see that this takes n square time, because at least about half the coefficients, n over 2 coefficients require n over 2 times, so it takes n square time. But what I'm claiming here is that using this discrete Fourier transform, you can actually multiply two univariate polynomials in n log n time. How do I do that? Here it is. So what do? I evaluate these polynomial on 2n roots of unity, and I told you using discrete transform how to do it in n log n time. When I write this n log n, I'm hiding the constant. Okay, these are like 2n log n or 3n log n. It's a big O of n log n. Evaluate the polynomial b again on the same 2n roots of unity. Do a pointwise multiplication of these terms. So what you have is in n log n time, you have evaluated the polynomial AB, the product polynomial, in these 2n roots of unity. Now, given the value of a polynomial in 2n roots of unity, there is a unique way you can get the 2n the coefficients of the polynomial. But here we have evaluated in these points. So the inversion turns out to be very similar to discrete Fourier transform. So it can be done in n log n. So you get the coefficients of the product polynomial in n log n time. Any questions? Okay, so this is one application of discrete Fourier transform, and this is exactly the application which we are going to use, and this is what is used in many algorithmic problems. It's even applicable for some graph problems, and everything boils down to setting up some two polynomials and argue that what you can pull out your answer from the product polynomials. Okay, any questions, comments? Okay, here is another application. Okay, you can actually multiply two n-bit integers in n log n time. This is something, multiplying two n-bit integers you learn in your high school, and you take the first one, multiply by this term, take the next one, multiply, do some shifts and add and so on. That actually takes n square multiplications, what you learned in high school. But using discrete Fourier transform, you can actually do it in n log n time. Why? Because if you have a number like this is actually, you can think of it as it's a 5 degree 5 polynomial, right? 7 into 10 power 5 plus 3 into 10 power 4 plus 2 into 10 cube plus 5 into so on. So it's basically evaluation of a polynomial of degree 5 at 10. You get this decimal number. So you take this number, state it as a polynomial of degree n, take this number, multiply using this algorithm, and then evaluate it at 10, you get the product and in n log n time. This is big news, because multiplying two n-bit numbers is such a fundamental problem that you can improve it substantially from n square. Now, there's one little caveat here. What is time here? Because I have to, if I am comparing with my n square high school algorithm, I have to be careful, because there I am actually counting the number of single-digit multiplications I'm doing, whereas here in all this FFT computation, you're multiplying by complex numbers, multiplying two pairs of complex numbers. Well, you can get around complex numbers, meaning you have some issues with precision, but you can get around that by actually going to a large integer ring, which actually has complex roots of unity. So you don't have to worry about precision, but still you will be multiplying large numbers, and it may be unreasonable to assume that actually takes, multiplying two one-digit number and multiplying two n-digit numbers. It's not reasonable to say that they take the same time. So this is one problem. But so if you actually worry about how many bit multiplication time it takes, it's the original thing. It took n log n times some polylog time, which is still much better than n square. But over a series of about 15 papers, now actually it has come down to n log n Boolean operations as well. Okay, so you can multiply two n-bit numbers in n log n time, and so this is all I need. And if you are with me so far, I've achieved at least about 50% of what I wanted to achieve. Now let's get back to our string matching problem and see how we can apply this polynomial multiplication to solve the problem. Okay, so again, first of all, let me just give you an intuition of how, what is the connection between string matching and this polynomial multiplication. Well, what are you trying to do in string matching? You have this pattern. You're trying to find various alignments of this pattern in the text. Okay, so actually you're trying to try and somehow in parallel try n alignments. What are you trying to do in polynomial multiplications? Well, as I told you, one coefficient is actually like this kind of products, and you're trying to compute 2n such coefficients. Okay, so it is, in hindsight, I found it very surprising initially that you can actually do Fourier transform to do string matching, but in hindsight it is not, because somehow it's all taking use of this power that these kind of n square kind of numbers, you can actually do it in n log n time. So our goal is to convert the string matching problem into one of multiplying two polynomials. Then we will use the polynomial algorithm to solve our problem. Okay, so here is the algorithm, and this is the 1970s work when Fisher and Patterson started talking about the string matching, applying FFT to string matching problem. So you have the text. So what we'll do is we'll create these two polynomials. First, these are the coefficients. So let's for now assume that there is only two characters, A and B. And later I'll tell you how to extend it to larger alphabet. So we'll create this polynomial coefficients. Ta is 1 whenever you have character A, and 0 whether it's B or don't care. Similarly for TB, similarly for the pattern. And we will construct this polynomial. Ta of x is summation. Take these coefficients and put an x power I on the side. And PB is slightly different. because pattern has only m length, so the coefficients you play around carefully. So P1 be x power n plus P2 be x power n minus 1, and you go up to x power n minus m plus 1. Now it turns out, okay, so here is T and P, and if you look at the coefficient of x power n plus k in this product polynomial TAX PBX, you pull this from the text, whatever the coefficient of n plus k minus I, and pull this from the text pattern x power n minus I. Then to simplify all this notation, coefficient of x power n plus k turns out to be P1b times TKa plus P2b TK plus 1a, and so on and so forth. Now, if you stare at this term, whenever the pattern is B and the text is BR question mark, this is 0. Because whenever the text is BR question mark, this term is 0. So whenever there is a pattern is B and text is question mark or B, this is 0. Similarly, this is 0. So what that means is that this number counts the number of BA mismatches in this text starting at position K. Okay, so counts the number of BA mismatches. Wherever the pattern has a B, the text has a A. Whenever there is a mismatch, this number computes this. So this is basically a coefficient of one term in the product polynomial. So now you try this for every K. So if you compute this entire product polynomial and pull out these coefficients actually tell you, number of BA mismatches. Now, similarly, now you run another FFT on the multiply TB with PA and look at the corresponding coefficients. You will get a number of AB mismatches. And now you can, from this, you will see that exactly where the text and pattern are aligned, even with this wildcard or don't care characters. Okay, so overall in n log n time, because it just involved multiplying two polynomials of degree n, you can actually find the entire alignment of your pattern with the text, including don't care characters. Now this works for two-letter alphabet. If you have multiple alphabet, well, you can actually do this for every pair of alphabet and allow a blow up of sigma square, which is okay if your alphabet size is small, maybe like in computational biology applications where you have 8EGC, there is a 4-letter alphabet, 16, which is not too bad. Actually, even this can be improved to sigma n log n. But theoretically, this presence of sigma was sort of annoying for a long time. People wrote a lot of papers because what I told you was a paper in 70s. And in 2007, Clifford came up with actually a much simpler, I don't know how people missed this, another FFT-based algorithm. So here it is. So let's now actually think of my alphabet itself as numbers, 1, 2, up to sigma. Then my pattern exists in the text starting at position I, if and only if this sum, Ti minus P1 plus Ti plus 1 minus P2 plus Ti plus 3 minus P3, this sum is 0. Is it true? Somebody should complain. Is it if and only if? So if the pattern exists in the text, yes, this difference, this sum at position I, this should give you 0. But there could also be cancellations here, right? Yeah? Was there a question?
No, I just said cancellations.
Yes, so cancellation can happen to give you 0 even if the pattern doesn't exist. So what you do is do some obvious thing, which is take the square of this. And you know that P exists in T starting at Ti if and only if this sum is 0. So now you expand it out, it turns out it's summation Pj square plus summation Ti plus j square minus this term. And this term looks exactly like what you can put it in two polynomials and compute it in n log n time. And you can verify that this is order m and this is order n. But remember, I'm only talking about exact string matching here. Okay, so for exact string matching, m plus n log n is no good because anyway, KMP can do it as good as much better than this. Okay, so now if I want to bring in don't care, so here is the simple solution they came up with. You add this value 0 for don't care, and now you change this equation to P exists in T starting at Ti if not only this difference square times. In fact, I can actually forget the primes here, just ti plus j minus 1 pj. So what does that mean? Either if the text align, the characters match, you will get a 0. Or if any of them is a don't care symbol, you get a 0, because this product will be killed anyway. And that's what we want, because if you have a don't care symbol either in the text or pattern, we want to say that there is a match. Okay, so once they observe this, you write it, expand it out, and it turns out to be something you can actually put it in some polynomials and compute it in order n log n time. Okay, so my final comment, this is the last slide. Let me just give you a little trick to improve from n log n to n log m, because remember, m is much, much smaller than n. Anyway, in the logarithmic scale, it's not so bad, but it actually turns out you can actually improve it. So there's a very simple trick.
Venkatesh, can I ask a question? Sorry.
Sure.
Huh?
Yeah.
Jam here. You're talking about with the alphabet. I missed the thing. Don't we still have a log sigma factor coming in?
No, nothing. So only problem you could complain is that these numbers are big now. So earlier we were dealing with ones and zeros. There is no log sigma because these numbers, I'm taking them as numbers. So I'm doing a difference on the numbers and multiplying them. So I'm just multiplying and adding numbers. There is no log sigma.
Oh, I see. Okay. Yeah, sorry.
Okay, so final trick from improving from n log n to n log m is that basically you break your text into overlapping strings of length 2m each. And then you align your pattern with each of these substrings. So this alignment will take m times log m, m times 2m log m, and we'll test all these. And how many times you're going to do? N by 2m times 2m log m. So you cancel out, the whole thing becomes n times log m. Okay, now this has been used also to extend to other problems like, suppose I want to find occurrences with up to k mismatches and so on and so forth. There are algorithms for this. Okay, so this, to summarize, I think this discrete Fourier transform is a very nice algorithmic tool, which is a lot of applications. And approximate string matching is another big, open, interesting area, and where FFT has been applied heavily left and right. Okay, I'll stop here. Thank you. Questions?
Thanks, Venkatesh. Yeah, are there any questions?
I have a short question, Venkatesh.
Yeah.
See, you mentioned about pre-processing.
Yes.
To make the effort simpler. See, how do you quantify pre-processing? Because that's like infinite. How do you?
No, it's not infinite. So suppose you have a text of length n. Okay, so imagine you have tens of billions of characters. So you organize your text and build some sort of an index, some sort of a data structure is what the correct term is, and that the time it takes is a function of the n, the text length,
which could be very large.
Which could be very large, but the point is you do that only once in a while. Remember, this pre-processing you do once in a while when the text changes, but the queries are like millions of queries every day all over. So you want to actually, care about answering the queries fast. Once in a while, you are willing to spend, it's the same thing about dictionary, right? You want to organize dictionary, or telephone directory. You want to organize your telephone directory. That happens once in a while. You organize it in a nice way that if somebody gives a name, you can quickly find the phone number, right? The queries are a lot more every day, whereas this pre-processing happens once in a while. So you're okay to spend more time, but again, when I say more time, it's not a huge amount of time. If you remember my slide, actually pre-processing in linear in the text you can do. So it's not a huge polynomial or anything.
Thank you.
Jam?
Jam, yeah, I have a question. Instead of talking about this don't care, supposing I actually want to look at the positions where the don't care is, or rather where there is a mismatch. The same kind of idea can work, right? I mean, I'm just
Yeah. So, I mean, that was the last bullet point I had, that if you say, given this pattern, I want to compute its occurrences in the text with up to k mismatches.
and you bound the Hamming distance of the mismatch or something like that?
Yeah. So, I mean, so your running time will depend on this distance. So you say a priori what is it you want, how much you are willing to tolerate, and your running time will depend on it.
I see. And what's the kind of dependence you have?
Oh, so not
again linear or
k square, k cubed, things like that. K is the Hamming distance.
Okay. Thanks.
Ravindran has
are there any other?
but I think that's an old.
Yeah, Ravindran, do you have a question?
He's not lowered his hand. Okay.
Okay, yeah. Amritanshu, you had something to say?
Yeah, I was just wondering. So if the pattern now is changed, is sort of keeps in you type in things one at a time, and your pattern grows. There's no way to. You have to again recalculate the whole thing, right?
That's a good question. So the other way has been studied. For example, if the text grows, okay.
Okay.
So, for example, text is coming in a stream, and you want to know whether your pattern matches up to a point, and then when the new symbol comes, and you want to know whether it matches with that text and where all it's coming. But pattern grows, I don't know.
So that looks harder.
Yeah, because much of these algorithms take the pattern, do some pre-processing, and then do some work. So if you don't give me the full pattern, I don't know. Yeah, maybe studies. I don't know the literature.
Thanks. No, this is amazing talk. Thank you.
Thank you.
So are there any other questions?
I have another short question.
Yeah.
Yeah, sure.
Venkatesh, in physics, we have something called lattice Fourier transform. And a one-dimensional version of it is your discrete Fourier transform.
Right.
So it's as if you have atoms forming a chain, closed chain. And you have some property associated to every atom and then you Fourier transform. Now, in physics, we have two-dimensional lattices and three-dimensional lattices. So are there generalization of lattice Fourier transform ideas?
I see, for multiple dimensions. Good question. I don't know, but possible. Yeah, I don't know really.
I think, isn't it just like taking a different abelian group? I mean, instead of a cyclic group.
I see. Oh, okay. It's
So there's a general theory of Fourier transform on any abelian group. So
I see.
Okay.
though I don't know about fast. So
You don't know about what?
doing it fast.
I see. Okay.
But probably some similar.
So nice talk, Venkatesh. One more thought. No.
Sure. Yeah.
Like the famous problem of prime number factorization. Can it be mapped into the string matching in some way? Is there any, or it's not a good question? Because you're also looking for some pattern.
No. Yeah. No.
Okay.
In fact, here we are actually trying to do the other way. We are mapping the string matching into some polynomial. I mean, factoring for some polynomials using polynomials may be studied. Yeah. But yeah, I don't know.
Okay. Thank you.
Are there any other questions? So if not, I had one question maybe. So in your string matching essentially you look for overlapping matchings, right?
Yeah.
So is looking for non-overlapping matchings also studied?
Won't it be actually easier, because once you match, then you actually shift all the way to the end of that match and continue. So I would have thought, I mean, I've never thought about it, but I think that would be relatively easier. Oh, okay. But maybe you ask for maximum number of non-overlapping or something. Then, then what I'm suggesting is some sort of a greedy thing. It may or may not necessarily give you the maximum number. I don't know. I'll think about it. Sure.
Okay. Yeah.